Welcome to this talk. It's a quantum computing survey. So if you are in particular interested in one of these topics, we can also organize an expert talk about some of the topics. So let me start with a brief survey of what you can expect. Now I will first introduce DLR very briefly, my Institute of Software Technology and my department. Then I will briefly introduce the DLR Quantum Computing Initiative. Afterwards, I will tell you about the quantum computing activities in my department, first with a motivating big picture and how we see the development in this area. And then I will give you details on our activities. Afterwards, I will present selected applications. These are in cooperation with other DLR institutes. It's not only in my department, but normally we are involved, but not in all of the applications. Yeah, and if we still have time, I can also say in the end, but this is just an option, something about the QC Solution Center in Hamburg. Yeah, German Aerospace Center, you will know, is something like the German NASA. It's first research center and does research and development in aeronautics, space, energy, transportation, digitalization, and security and safety. And most of this research is done in national and international corporations, for example, with the US NASA, but also others, French and Japanese space agencies and so on. We also act as space agency. That means we plan and realize the German space activities, and we are also a funding agency. We organize research funding and also administrate the projects. And in German, we say we are one of the biggest Projektträger. Yeah, DLR has more than 10,000 employees across 55 institutes and facilities at 30 sites in Germany. You see the sites here on this map. And we have also international offices in Brussels, Paris, Tokyo, and Washington. I'm with my department, I'm part of the Institute of Software Technology. And you see here topic areas in our institute. So it's all around software. So first, dependable, safe, and secure software systems. So in the round, I already discussed it's about rockets, rocket engines, rocket control for landing, for example, and so on. Then artificial intelligence. Here you see something in the picture, anomaly detection on German coast areas. So if there are problems, we will detect them via satellite data. High performance computing and quantum computing, that's mainly my department. Human system interaction and visualization, software and systems engineering, so the engineering processes, and digital platforms like platforms for the integration of codes, coupling of codes, and so on. So the structure of the institute has changed, so should also be new here for Georg and Gerhard. Beside my department, we have 3 departments now, intelligent and distributed systems in Cologne also, visual computing and engineering in Brunswick, and flight software also in Brunswick. But we have nowadays also many offices in Oberpfaffenhofen, additional offices, and also a big group in Hamburg. This especially for quantum computing. My department, High Performance Computing, has in the meantime 8 groups. You see here performance engineering for mathematical software, very close to what Georg and Gerd do here in Erlangen, and Melvin is involved and others. I have also very good students in the meantime from the University of Cologne in this group. predictive simulation software, scalable machine learning and scientific machine learning, two groups. So you see AI has become more meaning, it's more important today, and scientific machine learning helps to make it robust. Yeah, scalable adaptive mesh refinement, a special thing which is needed in many applications. We have with TED code one of the world leading codes in the meantime because it's very scalable onto a million processes, and also the partitioning is scalable. And simulation and optimization of technical systems, that is from geometry modeling, mathematically, parametric description of aeroplanes, flights, and space rockets, and so on, and from this optimization problems which have to be solved there. And most important for this talks are the two groups, quantum computing methods and implementation, and quantum computing applications. So we cover the whole software stack here. So our part is mainly software and algorithms, and here this is closer to the hardware, but this group does it's quantum error correction and mitigation, hardware-specific compilation, circuit optimization, realistic noise models, also hybrid computing. This means classical HPC plus quantum. In the more application-related group, we do quantum simulation, variational quantum algorithms, combinatorial optimization with quantum computers, but also mapping of optimization problems onto quantum engineers, onto the network, the connection network for the qubits. Yeah, a few words about our activities besides quantum computing. So in this department, we do a lot of things which has to do with classical HPC. And in the DLR context, this means simulation with digital twins for aeroplanes and helicopters, for example. Geometry modeling, I told you, that's what one group does. And here you see also you cannot see it remotely. Here you can also see the adaptive mesh refinement, which is extremely scalable. Then high-performance data analytics. This is something we do mainly with the Oberpfaffenhofen people. We develop predictive software frameworks based on statistical modeling and deep learning. For example, here, this is pandemic simulation, and below it's RNA design. So this is from third-party projects where we use exactly these techniques. Yeah, so let's come now. I forgot, for all these applications, we have a performance engineering part. So that's also normally a typical task in my department. So that means we look, as you do here in Erlangen also, on performance or at performance. Yeah, the DLR Quantum Computing Initiative, that's where a big part of our funding in the area of quantum computing comes from. It's funding together with industry. 80% of the funding goes to industry and 20% to DLR. We fund industry, startups, and suppliers, and do together research and development. We, in particular, work at the software stack for quantum computers. Yeah. We have two innovation centers there in Hamburg and Ulm. In Hamburg, there are 11 people from my department and many companies and also people from other DLR institutes. By the way, the funding was about 740 million euros from BMWK. for this activity. And currently we have 5 quantum computing platforms and 17 hardware and 20 software and application projects, and 20 plus industry contribution there. Here it's hard to read here. This is a survey. You can see it, let's say, afterwards on the slides. Let me just say here that we have different quantum computing architectures, ion traps, also analog computers. So in the DLR, we would also call it an analog quantum computer, nitrogen vacancy centers-based quantum computers, photonic quantum computers, and also neutral atom quantum computers based on Rydberg atoms. From the hardware, we also fund enabling technologies, develop software close to the hardware, middleware, and have many application projects. Let me just mention optimization here and material science. These are important projects for DLR. Later I will tell you more about. This here you heard already most of this. The projects are cover 100% of the costs. Focuses on hardware, software applications, and the ecosystem. And there are projects underway with a volume of several hundred million euros. Yeah, that's the goal. In the end, with 11 quantum computer projects, 5 qubit platforms, and participation of 19 DLR institutes and 22 industry partners. A few words about the Innovation Center in Hamburg, where also 11 people from my department are located. Here, the main hardware architecture is an ion trap system, and what my people does here is algorithms and compilation, mainly in a project called RWTH. And there are other projects regarding the ion trap system and the ecosystem for this. The project is called Toccata, this industry participation.
So that's one of the 5 qubit systems that you mentioned.
Yeah. In Hamburg, we will have also several systems in the end. So this is a system which is already running, which I mentioned here. In Ulm, a varied ecosystem at the Obere Eselsberg. There normally from DLR, the people who do quantum technologies are located. But there is an additional center now for quantum computing, but this fits very well, I would say. Here we have mainly architectures based on neutral atoms, NV centers, and photonic systems. Yeah, you may know the NV centers are based on defects in diamonds, and at the moment the system is there, it's installed, but there is a lot of noise in the system, and a lot of research is done to handle this noise at the moment.
What about this Akura quantum computer? It's an analog quantum computer. I thought all quantum computers were analog in a sense. So what qualifies it as analog?
I would not say so. So the gateways, I would more see close to digital. So our quantum computer is a different thing beside digital and analog quantum computers. Yeah, this is something like in the NELA here, a similar technology. We would call it like this. And I'm not totally convinced on this analog system, but it got a lot of support here. Yeah, and if you know the tradition of analog computing, I still had it in my study. You can solve with analog computers in a very fast way, for example, differential equations. So you just give a signal and the output is there immediately. It works similar, but I'm not totally convinced that it is still a good option today. But this system is also based on FPGAs, and this technology was at my study time not so evolved and elaborate as it is today. So let's see what the result is in the end. So I was not so optimistic in the beginning, but apparently it at least works. Here you see some of the industry partners, many startups and small companies, but also Fraunhofer. NXP is a chip designer, and we are in Hamburg. We are in the building of NXP. Yeah, at the moment, all these are involved here. Which is maybe more interesting for you are the projects, are these three projects we do here. And the big research topic here is reliable quantum information processing that depends on the error correction. And you see in the graphic above, in the graphic above here, this threshold. In 2020, we were about here. And here you see physical error probability. Here, this part is classical simulation. Then here was noisy intermediate scale quantum computers, and the AirKit project should in 2028 reach this point here. And later, you would have universally error tolerant quantum computers. And what we do in the project is enhancing the reliability of quantum information processing with novel error models. This is a big research area here, simulators for quantum error correction and new quantum decoders. So for DLR, an important application project is quantum mission planning, and solving such mission planning problems with quantum algorithms is promising. And and what is also challenging is creating an interface between classical and quantum planning tools. Contractor here is E.ON, and these activities are based on satellite data. Later, a little more about this. And I already mentioned the Toccata project. This is about building a user-friendly, reliable, and scalable quantum processor with 50+ qubits on the basis of ion trap technology. Yeah, and for example, we had this discussion before. Professor Osberghaus from Hannover is involved here, and contractor is Universal. Industry contractor is Universal. Yeah. Now, something about what we do in my department, and first the big picture, how we see the future and what we expect from quantum computing. So, background is the development status of quantum computers, and there was this study from the Federal Ministry of Security, Safety in the Information Sciences. Some of our people were involved in the studies. A big topic for quantum computers is quantum error correction. Universal quantum computers are intrinsically error-prone. Gate-based quantum computers are universal quantum computers. Quantum annealers are not universal. And for the implementation of killer apps, if we, for example, consider the classical Shaw, they require quantum error correction. Quantum error correction basis on redundancy. That means you need, it generates a significant overhead in required qubits and gates. Yeah, here in the graphic, you see the limiting error rate, and the threshold is in the order of 10⁻². You have then on the x-axis the number of qubits, and here you are in the part of classical simulation. Here is a part of near-term applications, and if the number of qubits becomes higher and the error rate is smaller, then you could really get useful error-corrected quantum computers for real-world problems. But this is still far in the future. So here we can already show quantum supremacy, but not for real problems in the order of 50 plus qubits, because you will know with classical supercomputers I can simulate about 50 perfect qubits. Here in this area, 100 qubits, we could already look for near-term applications. Here we have successfully introduced error correction, and here we have fully operating universal quantum computers. If I have 1 million qubits, then even difficult algorithms, for example, for solving equation systems or differential equations would work. And if we want to achieve quantum supremacy for real world problems in the near future, then it's only possible with noisy intermediate scale quantum computers. This means we have to live with these erroneous systems and to develop error correcting and mitigating algorithms. Today's NISQ machines are small, noisy, and have a limited connectivity. That's a fact. In the coming years, we expect quantum computers without complete quantum error correction. And the question is it still possible to achieve quantum supremacy or at least a distinct quantum advantage? So it is not possible to go from an application directly to the hardware. We have to do a lot of things in between. This, for example, is a gate scheduling problems. If you change airplanes at an airport, this is a complex problem. So you can solve it with a quantum computer. So for small problems, you can already realize it on a quantum computer. But to make it full working, there's a lot to do. And what we do here with my two groups in the department, we develop on the application side algorithms, optimization algorithms, variational algorithms, and quantum simulation frameworks to support this. And on the side more closely to the hardware, we develop compilation technologies and error mitigation, error correction algorithms, and something like that more later. And this is important for us to do a successful hardware-software co-design here. So, and in the Quantum Computer Initiative, we also see requirements from our solutions to quantum computers, and we can really collaborate with the hardware developers so that we get some improvement there. Last slide for the big pictures. So what about promising applications? So here it's the, and on the time, on the axis, either time or required error correction. So with time, error correction will improve. That's our expectation. So, and today we could also already be for atomistic systems, atomistic material design and so on, we can already use quantum simulation. This is possible with the systems we have today. Combinatorial optimization is already in the reach. Quantum accelerated machine learning. So this is something where I and the people in my department think this is something later in the future. It's not so easy to reach advantages here. Also, it's a topic which is interesting for many people, for example, also for Los Alamos, but it's very hard to get an advantage here. And it's even harder to support classical simulation, like solving Navier-Stokes equations or something like that with quantum computer technology, but people already do it. So there's no guarantee, it's just our judgment here, but that's our experience.
A question about the combinatorial optimization problems.
Yeah.
I know that there are companies, for example, who already use annealing methods to optimize schedules and whatnot. Is it really expected to have a quantum advantage for these applications?
Yeah, not a quantum advantage regarding exponential speed up. That is not the case, but you can solve problems in a better way. So you get better optima, for example. So because a quantum computer and especially also a NEDA will give you a global optimum. I can tell you for satellite scheduling, we had the project with Airbus, where we also used a NEDA implementation, and we thought, oh, this could be only a little better. But the solution, it was in the end a little better, but it was for Airbus, it was really a very good cost saving, even this small advantage. We were astonished that the advantage regarding the cost was so big. And Earth observation by satellites and controlling satellites is very costly. So there is already something you can gain also in the logistic area, for example, but it's difficult. But what we cannot show today is an exponential speed up. Or it's, from my experience, if we have not exponential, but a significant speed up, you can also improve the classical solution then with the knowledge. For example, all the annealer algorithms we developed resulted in better classical algorithms in the end. But that's a good thing. So I would say this is really fruitful if we reach something like that. Okay, some details about what we do in my groups. Yeah, we have two entangled sites in St. Augustin, Konrad-Adenauer-Stiftung. We recently moved to there. So that means that people are in Cologne, and there it's very close. So you can reach it with buses or S-Bahn and so on. And in the NXP building in Hamburg-Lockstedt. And it's one of the sites where the quantum computers are built. Yeah. These are the people. It's an international team. We work in projects about compilation, error correction, integration, also in the Archive project. In the Elevate project, we did training for the other DLR institutes and elevated the use cases from this project. A lot of the applications I will show later evolved, and we have also many Ph.D. projects regarding quantum computers. In my department, I have now 17 Ph.D. students. That's a lot for the DLR department, and 8 of them are in the quantum computing area. And we also have EU projects and BMBK projects, and you see that's always about error correction, compilation, industrial use cases. And this was especially a project for hydrogen generation. And here again, many companies and other research centers are involved. Saarland University, there's also Frank Wilhelm Mauch is involved. By that Düsseldorf University, they have also some good people regarding quantum computer. Fraunhofer from there's a combination with Bonn University. The goal in this department regarding compiler technology is several projects, one compiler. And the topics here is first circuit optimization, reduce the number of gates in a circuit. For small special circuits, find optimal solutions and take noise into account. In this group, we work hardware specifically. That means in one compiler step, it's important to generate only gates, because gates are also an abstraction layer native to the machine, and exploit features like a multi-qubit operation. We also consider the quantum computer as an accelerator for classical computers. We then use quantum computing only for coherent computations and develop techniques for hybrid programming. That also means we put everything which is possible to pre-processing and post-processing outside the quantum computer. The more we can do there, the more successful is the quantum computing part with today's small and noisy systems. Yeah, we also developed the whole stack and the access tools. You see here, these are users from DLR, from universities, from other research institutes and industry. We use the DLR technical infrastructure and organized by a tool access and orchestration. We access to quantum, to DLR's quantum computers and to DLR's quantum simulators, which are located on DLR's high performance computers, mostly in Dresden, and we can also use cloud platforms. Here, if we take the user view, then the user can use algorithmic libraries. These libraries also contain patterns for solving usual quantum problems, and the user can also edit these patterns. Then by the compiler, we can bring the application to our quantum computer and quantum computers, and if we get the results, the results are analyzed. And for a quantum computer result, you need statistical analysis to see if it's really good. It's not possible to trust only one result. So on classical computers, this is possible, but not on a quantum computer. What we do here, especially together with the industrial partners, is to develop unified interfaces for different QC hardware. So this is definitely something, a big benefit which will come out, which will be a good result from our projects and also for the quantum computing initiative. So if we reach that, then I think it's already a big benefit. Something like how we can mitigate noise. This is one technology, calibration of syndrome measurements. We find by several measurements, we find out what is the usual noise level on a hardware architecture, and we can consider this then for all results, and this improves error correction and noise estimation. We are also interested in benefits of small error correction codes and application-tailored quantum error correction. So, yeah, another thing is you asked for quantum advantage. So, and it's really not clear when a quantum advantage can be expected, or what makes a quantum computer powerful. We have to decide how quantum is an algorithm, which properties of quantum theory are required, non-locality versus entanglement, which use cases can benefit from a quantum computer. And we have also models for this and tools with which we can give decision support also for users, so that we can estimate if an advantage can be expected or is probable there. This tool is quite elaborate already, and Peter Schumacher was involved in this, and there's a very good paper about that. And there are also some promising proposals out at the moment about this. So it's more than it looks like at the first moment. It's more important. Then testing of quantum software. That's also very difficult. If you develop software for a quantum computer, then assertions are for finding errors and so on that are very difficult in quantum computers because they affect the state. Therefore, we use concepts from quantum error correction, e.g. Stabilizer measurements for finding errors. We apply them to crucial basic building blocks like state preparation, develop best practices here. In quantum computer and program verification is much more important than for classical computers because we'll not always get the same result from the quantum computer run. So therefore, people from computer science like that because it's part of formal methods there. Program verification is a big thing here. We can also use for small problems quantum simulators for comparison, because this is a digital thing which always gives the same result. Then I mentioned this here because this is something which should be more considered in the future, quantum computing performance engineering. So what shall we do? Are there performance models existing, or does it make sense to use special performance models here? Performance tests, how to do them. Benchmarking is a big problem here. And especially all of these topics here are very interesting for hybrid computing, classical HPC plus QC. Yeah, and if we do hybrid computing, then we have regarding performance and also regarding correct results, we have additional scheduling challenges. Many publications here, something about the more application related. Who you here in Erlangen, you definitely know Satoshi here, because we worked in other projects with him for a long time and is very successful in the application group. And with Benedict, you already did some performance engineering for a classical code, which was very successful. The research areas are digital quantum simulation, new algorithms for quantum many-body systems, and development of quantum simulation software for NIST devices. Combinatorial optimization is a big topic here, also around quantum annealers, but also about gate-based systems via the quantum approximate optimization algorithms. And with NASA Ames, we developed an open source library, Quark. There are other quantum applications and quantum-inspired algorithms, which we consider quantum machine learning, description of new quantum platforms. There's a Ph.D. projects, for example, topological quantum computers. This is just theory today. Microsoft is working on that, but there's no hardware at the moment. And state-of-the-art software for quantum computing benchmark. Yeah, this is the software we developed here in the application area. We have an application layer where we define the problem parameters. And here you have an optimization problem with constraints. So from this, we develop a problem description for the quantum computer. You see here that's a QUBO without constraints. The constraints are integrated into the optimization problems via slack variables in the library Quark. And then here we map this to the connection structure of the quantum computer by a complete graph embedding and distribute the weights accordingly. Here you see it again for with a little different workflow, because we have on the one hand the combinatorial optimization problem, but also use classical optimization in addition, then generates a QUBO quadratic unconstrained binary optimization problems or an easing problem, and then embed it with a quantum annealer or do circuit simulation via this quantum approximate optimization algorithms and use a gate-based quantum computer. Why I repeated it here is because from this we can also deviate expressive and structured benchmarks and use it in a benchmark database. For quantum computers, benchmarks are very important. Low-level and high-level benchmarks. This is, I would say, high-level benchmarks, but also on the lower level. It's also a fact, if you work together with industry, you get benchmarks, but the machine then only works for these benchmarks, and you have a little different case and it does not work anymore. Therefore, it's important to develop a structured benchmark database. This is another approach how to mitigate errors. So it's from the physical view. It's robust experimental signatures of phase transitions in the variational quantum eigensolver, mainly done by Benedict, possibly. And the trick here is to focus on some parameters for the problem description which are noise robust. And this approach is already successful also on current NISC systems, and we could show it. This is an older result. We have also new results, which we presented last week in Berlin. And if you use here the physical view and the physical understanding of the parameter, it's very helpful, and it really helped to use some of the current RWTH systems, for example. Here are applications already. Here in this application, this gives an overview on our whole approach for quantum computing. I do not have much time now, but I say little about applications here. We categorize our applications by the most promising quantum algorithmic approaches. This is quantum simulation and hybrid algorithms, combinatorial optimization, machine learning, and others. And the subject domain. So the subject domain is also influenced by the DLR needs. So therefore, you find here, for example, material simulation and battery research, because this is very interesting for us at DLR. But also energy systems, logistics, radar technologies, this is important, and more far-based cryptography, but we do that for our navigation institute, climate research and aerodynamics. Quantum simulation. This is, for example, interesting for vibronic structure and dynamics, interaction of electrons and molecular vibrations. This is vibronics, and it's very important in chemistry, and the interaction can be simulated by quantum computers. Atomistic simulation of engineering alloys. This is, again, in material science, and electron sphere in organic photovoltaics. The goal here is to develop new design principles for solar panels. These are all important topics for DLR. Quantum machine learning. This is in the trend of the current AI wave. Quantum state compression of hyperspectral data. This is something where we can get an advantage of a quantum computer, because quantum machine learning could here for the analysis of remote sensing data. Uncertainty in the calculation of glacial ice mass balances. Here, neural networks are currently used. The estimation of the uncertainty is very important here, and we can compare there the uncertainty for the classical and the quantum neural networks. Maybe we get better approaches here. System modeling and solar energy research. Supervision of solar power plants requires a quick analysis of data, and here quantum machine learning could help. And or most of my people see this is more something for the long term and not now or middle time frame. But many people in the world, and also some at DLR, do research in this area. Combinatorial optimization. This is something we are quite optimistic. Transmission expansion problems. They are for power plants, multi-robot, robotic fiber composite, lightweight construction, again, material science. This is something where in factories, multiple robots do this. They are, because it has a lot to do with combinatorial optimization, scheduling, and so on. Therefore, even optimization algorithms for annealers are successful. And this is also material science, loading optimization for autoclave processes. You know, an autoclave is something like airtight vessel. And within this, you harden structures. And if you harden more than one structure, this is difficult to do it right. And this is also a difficult combinatorial problem. Other algorithms you have to develop for ground motion estimation. If, for example, buildings move, you can consider this by satellite data, kind of space methods to determine the rank. There you can use Shor's algorithms, and quantum state generation with photonic quantum computers. There we have to develop new quantum algorithms, and we need a special approach here. Quantum mission planning, a big problem for DLR. Satellites need supervision from ground control, and you have to assign human operators to work shift. You can use here algorithms which are close to Grover, or schedule contact between satellite and ground stations. This is a problem very interesting for DLR, and also interference, battery simulation. here it's a multi-scale problem, and unto nanometers, there quantum computing is a way to go by quantum simulation variation of quantum algorithms, and in the later future also for solving related partial differential equations. Here you could use this what is it called, Harrow-Hessidim-Lloyd algorithm, but for this algorithm you need 1 million qubits if you want to do that. So you see it's far in the future. Yeah, antenna optimization. There's you have antenna arrays and have to find here an optimal source width where the signal goes. This is something which was really successful at the moment, and it's classical. You have an optimization problem regarding the total power here, and formulate a Hupo there via certain transformations. You can also regard interference between the signals and use certain methods to check the results. This swap test is in the quantum computer to compare states, and if you compare the states, you can find out if the result is okay. Also, a very good paper about this method. The method was supported by a theoretical mathematician, so he really found good ansatz for solving this problem. I thank you very much for listening, and if you have questions, I would like to answer them.
So what exactly are quantum neural networks?
Yeah, that's not so clear. So the advantage, first, most problems can be used by classical AI methods. So, and I would say they are not optimally used in most cases at the moment. So you should first concentrate on AI. So if data encoding is possible and efficient for the quantum computer, you can reduce compress the data for learning distinctly on a quantum computer. So you will have a much faster learning pace. This is an advantage to expect. The neural network, for example, would be the same as before, but these are advantages which can be expected. Okay. But the encoding problem is not solved, therefore I'm not so optimistic there. It's problematic for quantum computers. Okay. But for some cases, for example, amplitude encoding or something like that, or also with quantum Fourier transform and so on, you can do something. So it's, I would say, current research, and there are some promising approaches, but it will take time. Yeah, honestly, no chance today. So the people who want to solve big data problems with quantum computers, this is the wrong way at the moment. There are developments like quantum memories and so on, where it will at some time be possible, but at the moment it's not possible. And as I said also here for the neural networks, if encoding is successful, this is compressing data, then this is a preprocessing step then, and you will get then from big data only a small number of data into the quantum computer. Then it's a step forward for big data problems. But at the moment, encoding is not efficient. So it's more complex than the whole quantum computer operation then, and the complexity is so high at the moment that I see no chance at the moment. So it's not a big data analysis machine, definitely not. As you have seen, so from our judgments, it's really far, far in the future. But people already think about that. So, and HHL is something which would support that, but for HHL, you need 1 million perfect qubits. And you know we are far from that. So we made a master thesis about this algorithm because this algorithm is really great. So it's a great algorithm to solve an equation system in one step. But this has so many constraints, and you will also not get a solution vector after this one step, but a function of the solution. So for some radar problems, for example, you need a solution which is of the form x transposed AX. So it's one value you get. But and if you need this, it could be successful, but this will still take a long time. So that's too optimistic to solve PDEs now at the moment. So we could think about using AI methods for solving PDEs. That's something I would say more promising at the moment. Yeah, for example, for quantum computing, it was even not 5 years, it was 50 years before. So that in 50 years we will have. So why we can be optimistic for quantum simulation and, for example, combinatorial optimization. The reason is combinatorial optimization also runs on annealers, and annealers are stable at the moment, and you have something on the best machines 20,000 qubits. So you will not have exponential speed up, but you will have a speed up and a better solution. Therefore, you can be optimistic, and also runs on error-corrected small gate-based systems via QAOA. This quantum approximate optimization algorithms are successful. Therefore, you can be optimistic here, because you already get results which are valuable for researchers. I would not say for industry directly at the moment, but for researchers you already get good results there, and you come forward. For quantum simulation, the step is that you now develop frameworks where you separate the problem into quantum parts and classical parts, and this also works quite good. Benedict Pauseway, for example, had some very promising results here. For example, regarding superconductors, which were published in Nature and so on. Therefore, we are optimistic for these approaches. So I'm not so optimistic at the moment for quantum machine learning, and because we have to solve problems which are, we do not see how to solve them today. And for partial differential equations, that's even later in the future. There I'm also optimistic, because all these planning problems or scheduling problems you can solve with quantum computers, they are commercially interesting. And take Deutsche Bahn, for example. We always have the plan if there is a problem. They cannot adapt the plans for scheduling the trains and so on in a fast way. So if it's a problem here, and when there was a lot of rain here in Jülich, all other people in all other parts of Germany were also had also problems. An optimal solution for this would really be a commercial success. This would be a killer app if we could optimize path planner there. And in other areas, it's the same with these scheduling problems. For us, scheduling for satellites, as I told you, even this small advantage on annealer was already for Airbus a commercial success. So on the other hand, the quantum computer is not as expensive as a classical system. If the hardware is reliable, it's in another range of costs than a classical supercomputer.
Also powerful.
Yeah, also yeah,
it's much less.
Yeah, yes, it's a green computer, but definitely, yeah, in this way. So therefore, that's also the reason why so many companies are interested in that.